Energy and mass are two fundamental concepts in physics, but they are deeply intertwined. According to Einstein's famous equation, E is equal to mc squared, which tells us that energy and mass are interchangeable. But what happens when we successfully convert energy into mass? What does it mean for the universe, and what could this process look like? At its core, this concept arises from the principle of mass-energy equivalence, a breakthrough in physics. This principle suggests that mass is essentially a form of energy. This idea revolutionized our understanding of the universe, showing that the two are not separate entities, but can be converted from one to the other under the right conditions. Mass-energy equivalence means that energy can be transformed into mass, and conversely, mass can be turned into energy. In practical terms, we most often observe this when energy is converted into mass through high-energy processes like particle collisions or nuclear reactions. When energy is converted into mass, it's not just about creating something from nothing. Instead, energy is essentially filling a space that wasn't occupied by matter before. For instance, in particle physics experiments, energy from particles colliding can create new particles, which are essentially a form of mass. The process typically takes place at extremely high energies, where the conditions are intense enough to cause this transformation. One of the most striking examples of energy turning into mass occurs in particle accelerators. These machines accelerate particles to incredibly high speeds, creating conditions where their energy is so concentrated that it can manifest as mass. This is how new particles are discovered in these accelerators. Energy is transformed into matter in the form of subatomic particles like quarks or leptons. But what about on a cosmic scale? In stars, nuclear fusion is another example of energy creating mass. The fusion of lighter atoms like hydrogen into heavier ones like helium releases enormous amounts of energy. However, it also produces mass in the form of the newly formed atoms. Over time, as this process continues, stars burn through their fuel, converting energy into mass, and eventually becoming massive structures like black holes when they collapse under their own gravity. This conversion between energy and mass also plays a central role in the process of antimatter creation. In particle accelerators, when energy is concentrated enough, it can result in the creation of particles and their corresponding antimatter counterparts. For example, when high-energy photons collide, they can produce an electron and a positron, which are equal but opposite in charge. In this case, the energy of the photons is converted directly into the mass of the new particles. So, what happens on a larger scale when energy is successfully converted into mass? The key result is the creation of new forms of matter. This process is crucial in both the formation of particles in laboratories and in natural processes that occur throughout the universe. The ability to convert energy into mass has profound implications for everything from the creation of new materials to the possible future of energy production. At its extreme, if we could find a way to consistently convert energy into mass on a large scale, it could potentially solve many of the energy problems we face today. For example, imagine a future where energy from the sun could be harnessed not just as light or heat, but as mass, allowing us to create new forms of matter for use in industries like manufacturing, space travel, or even building entire structures from the raw energy of stars. The concept of converting energy into mass might seem like science fiction, but it's deeply rooted in the principles of physics that govern our universe. The limits of this process are still being explored, and researchers continue to push the boundaries of what's possible in particle physics and energy science. However, there are challenges. Converting energy into mass requires enormous amounts of energy and very specific conditions. The mass-energy equivalence equation is theoretical, but the practical application of this principle in large-scale processes remains a significant hurdle. The amount of energy required to create even a small amount of mass is staggering, and we're still in the early stages of mastering this concept. Converting energy into mass is not just a fascinating theoretical idea. It's a process that takes place in high-energy physics experiments within stars and potentially in the future of energy production. As we continue to explore the depths of particle physics, the possibilities of what can be achieved by harnessing the power of mass energy equivalence are limitless. We are just beginning to unlock the potential of this powerful relationship between mass and energy, and who knows where it will take us next. Let's dive deeper into how the concept of mass energy equivalence plays out in real-world applications, particularly in the fields of physics and energy generation. The interaction between energy and mass doesn't just happen in laboratories or theoretical models. It's something that shapes the very fabric of our universe, influencing everything from the formation of stars to the behavior of the tiniest subatomic particles. One of the most notable effects of mass energy equivalence is how it affects the nature of black holes. These are regions of space where gravity is so intense that not even light can escape. What makes black holes particularly fascinating from a mass energy perspective is how their formation can be traced back to the collapse of massive stars. During this process, the energy that once powered the stars transformed into mass as the star's core contracts under its own gravity. When a star's core collapses, the energy released in this process can be enormous. Some of this energy becomes mass, which, in turn, contributes to the creation of a black hole. The result is a dense, massive object whose gravitational pull is so strong that it warps space-time around it. In this sense, a black hole represents a point where energy and mass are inextricably linked, with the mass of the black hole serving as a direct product of the energy that once existed in the star. This phenomenon is crucial for our understanding of how the universe works on both large and small scales. It's not just about the creation of black holes, but also how energy and mass interact in the cosmos. For example, when we look at the processes that occur inside stars, the fusion reactions that power these stars are an incredible demonstration of mass energy equivalence in action. As lighter elements like hydrogen fuse to form heavier elements, like helium, the energy produced by this reaction is a result of mass being converted into energy. But equally, as these reactions continue, the mass that forms from this energy fuels the formation of new atoms and heavier elements. In a way, the entire life cycle of stars is a massive, ongoing conversion of energy into mass, which has far-reaching implications for everything from the chemistry of our planet to the formation of galaxies. Without these processes, the elements necessary for life, like carbon and oxygen, would never have been created. Mass energy equivalence is also important in the field of nuclear energy alongside stars and black holes. Nuclear reactions, either in the form of a nuclear power plant or an atomic bomb, are a direct manifestation of energy being transformed into mass. Both processes convert a minuscule amount of mass to energy, but it is an incredible amount, which could be harnessed to generate electricity. The mass lost in nuclear reactions is typically incredibly small, but the energy produced is immense. This is because the energy released is proportional to the mass that's lost, according to the equation E is equal to mc squared. In practical terms, this means that even tiny amounts of mass can generate a huge amount of energy, which is why nuclear reactions are such a powerful source of energy. In a nuclear power plant, for example, the energy released from the fission of uranium atoms is enough to generate electricity for entire cities. But on a larger scale, this principle is at the heart of the devastating power of nuclear weapons. On the flip side of this, nuclear fusion, the process that powers stars, is another example of mass energy equivalence in action. Fusion reactions occur when lighter nuclei, such as hydrogen, combine to form heavier nuclei, like helium. In this process, a small amount of mass is lost, but it's converted into energy. This energy is what makes stars shine and fuels their heat and light. On Earth, scientists are working on replicating this process in fusion reactors, which could one day provide a nearly limitless source of clean energy. In fact, if we could harness the power of nuclear fusion on Earth, it could revolutionize the energy industry. Unlike fossil fuels, which release harmful greenhouse gases, nuclear fusion would produce clean energy with very little waste. And the energy generated by fusion would be a direct result of mass energy equivalence, where the mass of hydrogen atoms is converted into the energy that powers our homes and cities. The concept of mass energy equivalence also has applications in particle physics. In high-energy particle accelerators, such as the Large Hadron Collider, particles are accelerated to speeds close to the speed of light. When these particles collide, their energy is so concentrated that it can create new particles, effectively converting energy into mass. These new particles may be unstable, but they give us valuable insight into the fundamental forces of nature. Through these experiments, scientists have been able to create and observe exotic particles, such as the Higgs boson, which were previously undetectable. The creation of these particles is a direct result of energy being converted into mass, and understanding how this process works can help us unlock the mysteries of the universe. On a more speculative level, the idea of converting energy into mass could have even more profound implications for the future. For example, some scientists have suggested that if we could master the ability to convert energy into mass on a large scale, we could create artificial matter, which could be used for everything from building materials to advanced technologies. Imagine a future where we could create matter out of pure energy, allowing us to generate anything we need simply by harnessing the energy around us. However, the practicalities of such a process are still far from being realized. The challenges involved in converting energy into mass are immense, and the energy required for such conversions is currently beyond our technological capabilities. Nevertheless, the concept itself remains an exciting prospect for the future of science and technology. The connection between mass and energy is fundamental to our understanding of the universe. As we continue to explore the boundaries of physics, we may discover new ways to harness the power of mass energy equivalence. From nuclear fusion to particle accelerators, the potential applications of this principle are vast and could shape the future of energy, technology, and even the very fabric of matter itself. So, what happens when we successfully convert energy into mass? In essence, it opens up a universe of possibilities. We could create new forms of matter, revolutionize energy production, and explore the deepest mysteries of the cosmos. The future of energy, physics, and even space exploration could hinge on our ability to harness the power of mass energy equivalence, making it one of the most exciting frontiers in science. The successful conversion of energy into mass is not just a fascinating concept in theoretical physics, but a process that influences various aspects of our universe, from the creation of subatomic particles to the behavior of celestial objects like stars and black holes. The energy-mass equivalence principle opens doors to a deeper understanding of the universe's most fundamental processes. At the most basic level, this conversion exemplifies the deep connection between two of the most important aspects of nature, mass and energy. Energy is not a static quantity. It can be transformed into matter, forming the building blocks of everything around us, from the smallest particles to the largest galaxies. This idea is more than just an abstract concept. It plays a pivotal role in scientific advancements and technological innovations. We see the process of energy transforming into mass in real-world applications such as particle accelerators, where energy from collisions creates new particles, and in the heart of stars, where nuclear fusion powers everything from our sun to distant stars. Energy is continuously converted into mass and back, driving the processes that sustain the universe and give rise to all forms of matter. Understanding this conversion process is crucial for the advancement of science. The successful conversion of energy into mass could unlock new sources of clean energy, potentially solving some of the most pressing challenges facing humanity today. It could also lead to breakthroughs in particle physics, unveiling new subatomic particles, or even advancing our understanding of dark matter and dark energy, two of the biggest mysteries in modern physics. In the future, as we refine our ability to manipulate energy and mass at increasingly sophisticated levels, we may witness entirely new forms of energy production, as well as the potential for creating entirely new materials out of energy. This could revolutionize everything from construction to space exploration. The ability to create matter from energy could, in theory, lead to advancements such as the ability to generate resources in space or build infrastructure on distant planets. The future of space travel, where resources are scarce and expensive, could be transformed by such technology. Even more speculative, the concept of turning energy into mass could also have implications for the theoretical design of advanced technologies. Imagine if we could manipulate energy to create complex materials or even entire structures from the energy around us, potentially leading to breakthroughs in everything from nanotechnology to artificial intelligence. However, while the possibilities are vast, there are still many unknowns. The amount of energy required to convert into even a small amount of mass is colossal. Current technology is far from being able to sustain such processes on a large scale, and the practical applications of mass energy equivalents are still limited. But the scientific community is making strides, and as we continue to explore the limits of physics, the potential for new discoveries remains enormous. Ultimately, the idea of converting energy into mass is much more than just a fascinating topic of study. It's an idea that touches on the very nature of the universe. It reminds us that our understanding of physics is constantly evolving, and that the most complex phenomena may be more closely connected than we once thought. Through continued research, experimentation, and technological innovation, the future of mass energy conversion holds the promise of unimaginable breakthroughs in both science and technology. As we explore new realms of possibility, one thing remains certain: the relationship between energy and mass is one of the most profound discoveries in the history of science. The ability to harness this connection could shape the future in ways we are only beginning to imagine.